Good morning, myself I'm R. Akshaya. I'm from CSIT branch. Today my Tech Talk topic is Spatial SQL, a query and presentation language. Abstract. Recently, attention has been focused on spatial databases, which combine conventional and spatially related data, such as geographic information systems, CAD or CAM or VLSI. A language has been developed to query such spatial databases. It recognizes the significantly different requirements of spatial data handling and overcomes the inherent problems of the application of conventional database query languages. The spatial query language has been designed as a minimum extension to the interrogative part of SQL and distinguishes from previously designed SQL extensions by the preservation of SQL concepts, the high-level treatment of spatial objects, and the incorporation of spatial operations and relationships. It consists of two components, a query language to describe what information to retrieve and a presentation language to specify how to display query results. Users can ask standard SQL queries to retrieve non-spatial data based on non-spatial constraints. Use special SQL commands to inquire about situations involving spatial data and give instructions in the graphical presentation language GPL to manipulate or examine the graphical representation. The need for spatial query language has been identified in several different applications domains of spatial databases such as geographic information system, GIS, image databases or remote sensing 1451. The usage of standard query languages for spatial data handling has been hindered by the lack of appropriate language support for spatial data. Query languages such as SQL, Q, or query by examples are insufficient for spatial data because they address only the particular properties of lexical data. Spatial data have additional properties such as geometry and graphical presentation, and the user must be able to address in a query language. The importance of spatial relationships and operators for spatial query languages have been recognized, and the relational algebra has been extended with the spatial operations to a geo-relational algebra. But a spatial query language must be more than the following simple equation. Relational query language plus spatial relationships, that is equals to spatial query language. More functionality was added to languages such as SQL, which combines QUEL and graphical presentation, with which interactive communication is encouraged, or GeoBase, which has a flavor of inheritance and propagation of attributes and values in generalization and aggregation of spatial hierarchies, respectively. Instead of developing an entire new query language from scratch, an existing database query language is extended with spatial concepts. As the host language, SQL was chosen, and the resulting spatial query language is called Spatial SQL. Guidelines for an SQL extension. The decision to exploit SQL as the backbone for a spatial query language was driven by the recognition of efforts to standardize SQL as the database query language. The reason for extending an existing query language was opposed to developing a new one was also influenced by the recognition that spatial databases contain both spatial and non-spatial data that will be the subject of user queries. Three fundamental categories of queries in a spatial information system can be distinguished. Queries exclusively about spatial properties, example, retrieve all towns that are split by a river. Queries about non-spatial properties, example, how many people live in Orono. Queries that combine spatial and non-spatial properties, example, retrieve all neighbors of the parcel located at 26 Grover Street. It is crucial for spatial query language to provide syntactical means for all three categories. Traditional query languages do so for the formulation of non-spatial queries. For example, the query for the number of people living in Orono may be expressed as the following SQL query. Select population from town where name, that is equals to Orono. The following concepts of standard SQL were specifically every query result in a relation. The select from where construct is the framework of every query. And third, predicates in the where clause was formulated upon attributes. Requirements for spatial query languages. Investigations of conventional query languages identified 11 crucial requirements for a spatial query language that are not covered by conventional systems. An abstract data type spatial with corresponding operations and relationships is necessary so that users may treat spatial data at a level identified independent of internal coding such as XY coordinates. Second one, the display of query results in graphical form as the most natural form to analyze spatial data. Allows for the presentation of the geometry of spatial objects and the visualization of issues that are related to spatial objects. Third, the possible combination of one query result with the results of one or more previous queries give rise to a dynamic interaction. Fourth, graphical presentations frequently require the display of context, that is, information that was not explicitly requested, but that is necessary to interpret a query result in its spatial location. 5. Induced by the combination of multiple query results in a single rendering. 6. An extended dialog using pointing devices for selection by pointing and direct selection of a substance promotes the use of query results as a reference in upcoming queries. 7. Varying graphical presentation of spatial objects and their parts, described in terms of colors, patterns, intensity, and symbols. 8th, a descriptive legend is needed that reflects a summary of object classes displayed together with their particular graphical presentation. Labels play an important role in the understanding of drawings, and users must be able to select objects to be labeled from the query language. 10. Users of conventional maps have developed significant skills to interpret the actual size of objects drawn, and the selection of a specific scale of a rendering allows users of computerized spatial information systems to produce maps on which they can continue to apply their capabilities. Frequently, users work on a substance, not on the whole spatial database, and the query language must offer them tools to restrict the area of interest to a particular geography to which all upcoming queries will refer. Spatial SQL. In spatial SQL, the domains of the relational calculus are extended by the new domain spatial to provide a high-level abstraction of spatial data at the user interface. Besides the spatial domain and its dimension-independent specializations, the spatial operations and relationships and a method to refer objects on drawing by pointing at them with the direct manipulation device are introduced. This part of spatial SQL is extensible so that new spatial operations can be added into this conceptual framework. Specification of the topological relationship neighbor between two objects A and B in terms of the 4 intersections between boundaries and interiors as displayed in table. Spatial domain. Spatial domain provides a higher level abstraction of spatial data and extends the domain in the relational calculus by 4 spatial domains: spatial O, spatial 1, 2, and spatial question, for 0, 1, 2, and 3-dimensional spatial objects respectively. These domains are generalized to a dimension-independent domain spatial. An attribute over such a spatial domain is referred to as a spatial attribute, and a relation with a spatial attribute is called a spatial OR relation. Only the specified spatial operations and relationships apply to the spatial attributes. The figure shows the examples of the binary topological relationships, that is, first describes disjoint, second describes meet, third describes overlap, fourth describes covers or covered by, sixth describes inside or contains, and seventh describes equal. Spatial data definition. The data definition in SQL is extended for spatial attributes. The following example shows the definition of the relationship with a conventional attribute name and a spatial attribute geometry. Conclusion. Spatial SQL is characterized by minimal extensions to SQL and the introduction of the graphical presentation language. The 11 requirements of a spatial query language are satisfied. Several features of spatial SQL have an object-oriented flavor, such as a complex abstract data type spatial and its subtypes for different spatial dimensions. Recently, object-oriented SQL versions have been proposed as general and HOC query languages for object-oriented databases. Example: OSQL for Iris HDBL and 2 query language. HDBL and OSQL allow users to define complex data types, including generalization, hierarchies, and corresponding operations. However, the extension of a database language with a new abstract data types. Spatial SQL and GPL commands are verbose if a user has to type them from a keyboard. Considerable increase of the usability of this spatial query language is expected by incorporating the command line structure into a human interface as proposed. The incorporation of the direct manipulation device into the query language is a first step toward an improved interaction with maps using pointing instead of typing. Operations like pan and zoom are good candidates to exploit this concept, for which appropriate metaphors are being examined. Likewise, the implementation of GPL as a visual language is likely to boost its usability. For example, instead of typing a name for a color or pattern, users may make their choice from a control panel which represents a series of colors and patterns and also allows the users to create new ones. A cartographic editor to create and manipulate cartographic symbols is an essential component of such a user interface. Finally, the visualization of prototypical spatial relations may reduce the time learning a specific terminology and help users in the selection of the correct configuration. Thank you.